And welcome back. It's been some time since the last video, hasn't it? I've been very busy. I do actually run a repair workshop, mainly doing audio repairs, and that takes up my time, and it's been very busy. So we actually have a repair workshop running in the background, which I don't really cover on the YouTube channel. So anyway, we're back. What I wanted to do in this video was to continue with the radio repeater project featured in a previous video. And if you remember, we had a CPU card which I designed 1985, 1986, something like that, in a previous video. And lo and behold, if you remember, we ended up with a brand new version of that card. Yeah, so that's the new repeater card. Now, that all worked. That's all in the other video. As far as the audio card goes, on this card you've got various circuitry to take care of the analog signals from the radios, both on the receive side and on the transmit side. And this basically, if you like, is an audio interface which connects the two radios together. Now, back in the day, repeaters used to use a tone burst to activate the repeater. Without that tone burst, the repeater wouldn't switch on, and it was a safeguard against, spurious noises that might be picked up on the band, or other radios that don't have a tone burst fitted. You may not want them to activate the repeater for whatever reason, so you would use a tone burst. Now, the tone burst originally was a frequency of 1750 hertz, 1.75k if you like, kilohertz. And that was the injected tone that the transmitter would send. The receiver at this end would pick it up, and this phased-out loop would detect whether that tone was present or not present. Right, so that's the old way that it used to be done. Now, the thing is, this system's not been in use for some years now. All of the repeaters, especially certainly in the United Kingdom, and I'm sure in most other countries as well by now, have done away with this system. They now do not use the tone burst system of 1750 hertz to activate the repeater. That's now been replaced using CTCSS. Now, CTCSS is a bit similar to this. It is a tone coming in, but it's a completely different frequency. It has a range of possible frequencies between roughly 60 hertz and 250 hertz. Sub-audio, in other words, below what you can normally hear easily. In our new design, we have to replace this circuit, do away with this, and design a CTCSS decoder. We've managed to come up, just looking around on the internet, we've actually come up with a solution for that, for our CTCSS decoder, to replace this. And it's quite cheap. I think we can do it for less than £5 or something. It's pretty cheap to do. So yeah, it's an easy replacement. Now, in the United Kingdom, there's just been a law change to the amateur radio licensing specification, and it allows any amateur to operate a test repeater from home. That's wonderful, because it means when this is all finished, we'll be able to physically connect this to radios, and I've got to sort out a couple of aerials outside as well. I may even just do some tests using crossband radios just to get it to work. But the point I'm trying to make is it's now legal for me to do this using my own home call sign, G0BZY, and it means we can put it on the air, and we should be able to do some actual radio tests with a couple of the local hams in the area here. So the next thing we need to do is to address this tone detector and come up with a circuit to make a CTCSS decoder. So this is our first attempt to see if we can decode CTCSS tones. What we've got here is an Atmel development board connected to a display. Now, the software for this is public domain, and I've made some alterations, but basically the whole thing is copyright free and free to use. So I didn't really have to write any software, just loaded it in and away we went. Coming through these cables here, through these croc clips here, that's going up to the signal generator, and we're coming out of the TTL output. And the reason why we're coming out of the 5V TTL output, square waves in other words, is because we've got no signal conditioning yet going into the microcontroller here. So, and I can adjust this just here. I can adjust the frequency to whatever we want. If I say set this to one of our local repeater channel CTCSS tone frequencies, it's the local one where I live here is 118.8, 118 or 118.76, and I'm looking at the signal generator over there, and it does actually say 118.7, and this is saying 118.7.78 in fact. So the frequencies are correct. It's telling us that it's looking for 118.8, which is one of the, it's recognized that as one of the channels. This other information we can ignore for now. That's debug information coming from the software. Let's alter it, and let's go down a little bit. You'll notice when it's an invalid frequency, it just says no CTCSS, it's not valid. But if we keep going and hit the next channel, there you go. So we're putting 111.3 in, and it's recognizing that, or locking on if you like, to 110.9 Hertz, which is a valid CTCSS frequency. And all I'm doing is just adjusting the signal generator, and we're just injecting it with different tones. Let's try 200. There you go, 119.5. So I'm injecting 118.2, and it's locked on. It's within, within the specified area, and it's giving us 118.8 lock on. So I can adjust this to 118.8. So what's happening here is we are injecting the signal here, 5 volts TTL as I said earlier. So the next thing we need to do is probably we need to include some kind of signal conditioning and not just drive this with 5 volt signals. Here is an overall view of what the project is all about. This is our repeater project in block form. So we'll have 2 radios here, a receive radio RX, transmit radio TX there. Pretty much everything in red has got to do with the transmit side, and what's in black is on the receive side. So from the radio we'll have 2 outputs, a sub audio discriminator output, which is a full spectrum audio output from the radio. There's no filtering from the discriminator there. We also have a busy line or squelch line, which detects the presence of a carrier. Okay, so this is our CTCSS decoder, which detects the sub audio tone that we're tuned to. This can be set up for any channel that you like using programming pins. We'll have our CPU card. On the transmit side, coming from the card, we have 3 signals. We have a mute, the CW keying line, which actually sends the Morse code itself by turning the oscillator on and off. And we've also got a TX line, or PTT line if you like, and this actually puts the transmitter into transmit. So I'll deal with that pin first. So from the TX line, it goes to just a simple transistor switch, and then that actually puts the radio into transmit on the PTT line. On the CW side, you'll notice we've got a CW oscillator, and we'll have a couple of switches down here, and this is part of the 4066 switch package. There's actually 4. I think we're only going to end up using 2, and the other 2 will be spare, unless we can think of a use for the 3rd or the 4th one. So from the CW oscillator, it first goes to this switch here, which has got a little preset across it there just for simplicity of the diagram. And the mute signal controls how loud the signal is or how big the signal is. Either it's a full strength signal from the CW oscillator, or it goes to a preset to reduce the audio level. The next switch coming from that, there's another switch here, that is keyed from the CW output from the CPU card. So this is sending Morse code if you like, and that's turning on and off the signal from the CW oscillator, whether it's loud or quiet. Coming out of the last switch, that's then our CW, which then goes to the audio input on the radio transmitter. That's actually what sends the audio tone that you hear on the transmit side. There's also, you'll notice, the all-important audio path, the audio path coming from the radio through some sort of level adjustment which then gets mixed, if you like, and that all goes into the audio input on the radio. And that is pretty much the block diagram of the whole project. What we want to concentrate on next is the side tone oscillator for the CW ident, and this typically is an audio sine wave that we need of around 800 Hertz or so. What I've done here is I found a bit of a lashed together schematic. It's a phase shift oscillator circuit, and using an LM324 forms this entire oscillator, and you do indeed actually get a reasonably clean sine wave output. It's not 100% perfect, but you know, good enough for audio purposes. I've added a little buffer amplifier on the output here, because the output from here, which is a sine wave, is only about 150 millivolts peak to peak. It's a little bit small, so I've made a little ×10 gain amplifier there, which gives us roughly 1.5 volts peak to peak output at around 800 Hertz, and that's absolutely perfect. Basically, it's in here, this part of the circuit here. That's the LM324 quad op amp, and of course the whole thing is running on 5 volts only as well, which is an improvement from the old board. If you remember, if you watched the original video that we did, it needed a -5 volt rail, and I've decided it would be good if we can get rid of that and run the whole thing off 5 volts. And what I've done is I've just connected it through a little resistor. I think it's about 27 ohms or something like that, and I've connected it to a speaker so we can actually have a listen with a little bypass cap. It's all a bit thrown together, but anyway, I hope you can hear that tone. So that's our CW ident coming out of the or CW anyway, not ident yet. And now that we've got a side tone oscillator, which did away with the original chip that we had, which is an NE566, just to show we have actually got a clean sine wave, and it looks pretty good there, reasonably clean. So here we are back at the bench, and we've made some progress. Changed the software for the Arduino to allow basically removal of the display. The LCD has now been removed. We basically have a binary select port now, where you can actually set bits 1 to bit 6, and that allows the program to select which CTCSS tone you want to detect, and the output from the whole software from the Arduino is driving this single red LED, giving us a signal of whether the CTCSS tone is present or whether it's not present. So that's kind of what that's doing. So we've modified the software, display is gone, and we end up with a single LED. That's our logic state, which will go to the controller card. Right, there's also a little bit more analog circuitry here. We've got some op amps here. It's LM324, and it's configured in such a way to give us a low pass filter which cuts off at around about 288 Hertz. Anything lower than that goes through, and it rejects anything above 228 Hertz. So anything, let's say 300 Hertz up over within the normal audio range, is rejected. So it's only allowing through the CTCSS tones in the sub-audio region. We're also driving the whole circuit here from the IFR 1200 spectrum analyzer. We're not using it as a spectrum analyzer, we're only using it as an audio generator. And the reason why I'm using it as an audio generator is because it has a very precise audio generation system built in, down to fractions of a hertz. This in turn has a very accurate internal crystal oscillator oven. It's actually very good as a standalone reference, but just to be doubly sure, I am actually driving it from our GPSDO. It's completely locked. That's given us a very precise 10 megahertz reference signal, and that signal's coming here to drive the IFR. Okay, so I hope you can see this this little red LED here. It's a bit small on screen, I know, but at the moment it is on. We've got this programmed here for the BCD or for the binary to select a particular channel, and right now we are selecting channel 16 is the one we're selecting binary, and that means we are listening for or detecting 110.9 Hertz. That's what we're aiming for, 110.9. So we've actually got 110.9 sine wave coming out, and again that comes out of the audio, the tone out socket there, and by adjusting the frequency of the generator, we should be able to see this change state. So what we can do is we can alter this and say take it up, so it's 111 Hertz, still red, still red. I'll keep going up until we lose the LED. It's just starting to give up now, so that's right on its limit, and that's 111.9 Hertz. So that's an undetermined state. If we go any higher, I'll just keep going up a little bit. The LED's almost off completely at 112.3, 112.6, it's gone. So that's the upper limit of that particular channel. We've hit its limit. So let's go the other way. Let's go down. I'll just keep going down. Okay, that's going down to about 110 Hertz, and that's an undetermined state, about 110 Hertz. 109.7 Hertz, something like that, and it's gone. 109.8, and we're getting the odd flash, so that's on the border. So we'll put that back to 110.9, and I hope you can see that by going up in frequency and going down in frequency, we're more or less in the center. It's pretty accurate. It's not exactly correct. I'll change the frequency of the firmware, if you like, or the detection frequency, by changing the binary code, and I'll be back in just a second to do that. Okay, so just like magic, I've changed the binary code driving the firmware, and we're now presenting it with channel 3 or binary code 3. So it's like 11000 going from right to left. So it's channel 3. Now if you look at the chart for channel 3, we should be getting detection at 71.9 Hertz. Okay, 71.9. So let's try that. 71.9, enter, and there we have it. Then the LED is on. I hope you can see that. LED is on. We have a detection at 71.9, which is channel 3. If I just change the channel here, just by messing around a little bit, change the channel code, you'll see the LED go off. There you go. So we've changed channel, and it's not detecting the tone that we're putting in. I'll put it back again, and there we are. LED's back on again. It's got about a ±1 Hertz detection range. So 71.9 should detect up to 72.9 and down to 70.9. So that's the range. It's like plus a Hertz and minus a Hertz. The last thing I'm going to mention about this is I've compiled the firmware and changed the fuse bits of the Atmel 328P microcontroller that we're using here, and we're not using the onboard 16 MHz crystal. We've managed to actually get this to work with the internal 8 MHz crystal inside of the, or resonator inside of the unit. It's less accurate, and I think it's a bit more susceptible to temperature drift. I wanted to try a comparison between using the internal oscillator and using the external 16 MHz crystal, just because it means if we can get away with using the 8 MHz internal, we don't need an onboard crystal. It saves a part on the board. So everything seems to be working. We've got our detection, and I suppose that's pretty much that block complete and tested. So we've got diagrams, we've got working firmware for the chip, and I think we're ready to go at the next stage. Okay, so next progress. As you can see, I've put together a new design here on the perf board, and this is basically we've took it from the original design that we did earlier and converted everything and put it onto this new bit of board. So it's been transferred onto this new bit of board here. As you can see, I've also put the Atmel 328 microcontroller chip on board with a little crystal there, and I've been experimenting with using the internal oscillator only inside of the chip, which means we could get rid of the crystal. It does work, but I'm not getting as reliable tone detection. So that's basically given us our CTCSS decoder. You'll notice I've got some soldered pins on this side here, which allows us to select the CTCSS tone that we want. Right now it's actually wired up for 118.8 Hertz, 118.8 Hertz, which is the local standard where I live here in the northeast. And here we have a quad op amp, LM328, 5-volt supply for that, just a single 5-volt supply. We've got like a low pass filter coming in here with some other components to basically give you a digitized output to drive the there's a square wave comes from this that drives the input pin, actually the interrupt input pin on the 328. This connection here is our discriminator output from the radio. So this handles, if you like, full AF audio frequency bandwidth without any filtering from the discriminator, and that's coming straight in here so we can detect the sub-audio tones. Now you'll notice I've actually got the board wired up to our original repeater card, so that's come back out of the cupboard, and we've got this wired up with a couple of LEDs. This LED here is just showing the output of the decoder. It's actually active low to drive the card, so I've had to change the software a little bit to make it drive the card with a low signal rather than a high signal. Basically what's happening is the LED is in a normally on state. That means it's not decoding, everything's back to front. This LED here is showing the CW ident coming out of the card. You'll notice I've got a little deconnector thing going on here. That's basically wired from the back of the radio, because the radio's been slightly modified to give me these signals. So we've got discriminator output from the back of the radio here, and also squelch line or busy line. That comes to this deconnector, which means we can extend this easily with a normal cable, and that can then connect through to the audio card when it's complete. So that's as far as we've got, and I'll show you what happens when we inject a signal. Yeah, so I'm using the IFR again, and we're generating an output. This time we are using it as an RF generator as well as an AF generator. So our RF frequency I've got set to 145.4 megahertz, 145, 400, and that's actually going to be transmitting through to the radio, which then sends the signals to the repeater card. So I just need to adjust the radio to 400. There we are. The IFR actually has a microphone input on it, plugged in to the front there, so I can key this up, and we can send a sub-audio tone on that frequency to activate the repeater. This is our LED here. I'll zoom in on that in a moment, so we'll just key this up. There you go. If you can see that. Okay, I'll just zoom in on that a bit. There you are. 1, 2, 3, 4, 5. Just talking at the microphone, makes no difference. Now this isn't on the air, it's not actually transmitting or anything, but you can see that the card has activated and it's sending its CW ident. And that's because it got both the squelch or busy line activated, and it got the CTCSS signal from the decoder as well. So that's looking really good so far. The next thing we need to look at is expanding the card so we can handle something on the transmit side as well. That means we need to build a side-on oscillator at around 800 Hertz, between 700 and 800 Hertz, and we need to build some sort of switching for to route the audio signals. So that needs to be handled, and what I'm probably going to do is just take another bit of this board and build it on there, and we'll stick this on here, and probably I might trim this down. It's too big really for what we need. And then maybe it's just soldered onto this card here and make it bigger. Really liking this stuff. You get it off of eBay and places like that. It's not expensive. You normally get them in packs of 10 and stuff, and all it is, you know, it's soldered islands, if you like, per pin. It's not copper strips like Vero board. It doesn't connect all the way through, and I'm finding this stuff really handy these days. I'm using quite a lot of this for prototyping, so yeah, little tip there. And it's pretty cheap on eBay. So you know, really we're actually doing quite a few changes from the original design. Tone burst circuit's all gone and replaced with the CTCSS decoder. Oscillator is going to be replaced so it can run on a single 5-volt supply, and the 4066 is pretty much the only port that's going to remain the same. So it's quite a few changes to the original design. This is the oscillator, CW ident oscillator. So the board's not finished. I've still got this area here to populate, which is going to be for the 4066. I've got ridiculously big capacitors in here, physical size, I mean big capacitors. They just need to be 100 NFs. These are all I had lying around, you know, so without getting into surface mount. So basically I've just stuck them in. And let's have a look at the scope and see what it looks like. Yeah, output looks pretty good. It's not a perfect sine wave, but it's pretty damn close. I'm just using the IFR as basically an audio amplifier. This is our signal from the oscillator, so we can just like hear what it sounds like. Right, switch it on. That's what it sounds like. Just touching the probe onto the output of the chip here. It's a little bit low. I think the pitch is like a little bit low. We can adjust it and make it go higher if we wish. So I just want to give you an overview of what we've got so far. Here's our 3 boards. These 2 boards are going to be eventually one board. So I'll show a close-up of that in a moment and explain what's going on now. Just an overview. So I've got the IFR plugged in again. This time we're actually listening on air, RF, to 145650. That's 145.650 megahertz. Just using that as a sort of like as a transceiver, as a radio. It also has a microphone so we can transmit and talk through it as well. So that is listening to our transmitter radio, which is up here. So this is tuned to 145650, same as the IFR. That's transmitting. At the moment it's very low power, it's about 1 watt into a dummy load. So there's no aerials connected at the moment. This is purely just all dummy load, local testing in the shack here. The receiver, which I showed earlier, which is connected through these D connectors, and that goes to the various logic board, like the controller, and also to the analog board as well. Okay, so here's the 2 boards. So we've already looked at the CTCSS decoder board. That's it there. And the LED's on at the moment. Don't know if you can see that very well. That's the output of the CTCSS decoder. So this board here, you've already seen the sine wave generator that we used for the CW generation, with these rather large capacitors. It's all I had lying around. We've also populated this area here. This is new. Let's have a closer look at that. Yeah, so here we are. We managed to reverse engineer the switching circuit, the audio switching, or the audio routing if you like, from the original card. Once you know the pinouts of the 4066, it's not difficult at all. So here we are with our 4066 here. You'll notice there's a few preset controls. There's one there, another one there, another one there. So this preset here is adjusting the mute level. When the CPU card sends a mute signal through one of these wires here, it basically reduces the audio volume of the CW ident, so it's kind of in the background while somebody else is talking over the top of the repeater. This control here is the overall CW level. So basically, when it's at full volume, which is how you would calibrate this, when it's not being muted, this sets the deviation to the transmitter for the CW level, so you can make the CW any level you like. It's best not to have it too loud. And this preset here is the audio level from the receiver radio being rebroadcast through to the transmitter radio. So this is voice, if you like. That's the audio level for the voice. So with these 3 controls, and these 2 are a little bit interactive as well. It's a very simple resistor mixer. There's nothing active here, so the resistors do actually affect each other. So you need a little bit of fiddling backwards and forwards, but eventually you get it balanced out and it sounds correct. This little bit of circuitry at the back here, it's just a key-in transistor, which basically turns the transmitter on and off, again from a signal from the control card. Right, so moment of truth. Will it work properly? Right, so now we're going to try an on-air test. I've actually got the radio connected to the external aerial, and you can see the diplexer for the VHF and UHF combination there at the back. And right, so let's see if we can have a QSO with somebody. Let's give this a try. So I'm having to manually adjust the volume to stop the feedback. That's just a limitation of working crossband. G4LIA, G4LIA. This is G0BZY listening.
Go ahead, Paul.
Ah, that's better. I can hear you a lot better now, and should be coming across on the camera better as well. Yeah, thanks, Joe. And yeah, you're a good audio into the repeater. And so, what's my audio like at your end? Go ahead.
Yeah, absolutely fine. No bother at all. In fact, what I should do is press some buttons on here, and I'll just press record start, and then see what turns up in terms of the record. G0BZY, G4LIA with a load of waffles for audio recording purposes.
Yeah, G4LIA, G0BZY. Okay, Joe. Yeah. There's a little bit of noise on your signal, but totally readable. I'd give you about an S5, looking at the S meter there when you were talking on the repeater radio. So yeah, looks like we're up and running, and like I say, I'm getting a better audio quality now at this end for the camera. So should be audible. Last time it was across the other side of the room, probably wouldn't have heard a thing. So that's a lot better. And aye, very good. Well, it's been a good test, and see what it. Let's see what we're going to do next. I'm not too sure what the next plan is from G0BZY.
Yeah, from G4LIA. Oh, we'll have to have a word with yourself then about the forthcoming plan.
Ah, and the battery in my radio has died. Whoops-a-daisy. Okay, well that's the end of that test then. So we'll make that the end of the video, and I think we've shown that it all worked. We've had a real QSO there with my buddy Joe, G4LIA, which was kind enough to come on the air and do some tests with me, and we've shown that the whole thing works. I think the next video we might be looking at taking the electronics and doing a PCB perhaps, and putting it in a box. Now I've got a nice project case and everything, and I'm thinking, tempting to just actually finish this off, PCB it, and we'll do a bit of KiCad with that, bit of design, and put it in a case, and that'll be the end of the project. And we've had an on-air QSO over the radio. So I hope you've enjoyed this. If you have, give us a thumbs up, hit those buttons, and subscribe if you want to see more like this. Hit subscribe, hit like, all that kind of business, all that sort of jazz. And thanks very much for watching. Hope you've enjoyed it. Till the next time, bye bye.